Good morning. So I want us to give an introduction to data assimilation in 3 lectures. So today I'm going to talk about some of the basic theory. Tomorrow I'll talk about how pick a couple of particular algorithms for solving the data assimilation problem that we use in practice. And then on the third day we'll use look at some examples of current challenges and some practice of data assimilation. And there will also be tomorrow and the day after a couple of practicals associated with this. So what is data assimilation? We've seen a lot about all this data that we collect from satellites, etc. And the question we're interested in is how we can use this data, combine it with our models to really get an understanding of the Earth system. Because often the data we have are not enough on their own, either to really get an understanding or to initialize a forecast. So for example, if we want to initialize a weather forecast or an ocean forecast, we need to initialize at each point of our grid point model the value of the temperature, the value of the wind, the value of the humidity or whatever at each point using the data we have in order to make a forecast. So data assimilation is the process of taking the observational data we have and combining it with some information from our model. So usually an a priori state, a previous estimate of the state, which may come, say, from a previous forecast, combining with this with the data to understand what is the situation of the atmosphere now, our best estimate of the atmosphere or the ocean or the ecosystem, etc. now, so that we can make a forecast or use that to understand some processes. And in doing this, we want to make use not just of the data, but also of what we know about the system. So we want to make use of the system dynamics, known physical properties of the atmosphere, and our uncertainties in the observational data. So this is just an example of the ozone hole in 2002 over the South Pole. On the left, you have the data from the satellite measuring the ocean. And on the right, you have the product of data assimilation, combining this data with a model forecast. And what you can see, the blue on the right, is the areas of low ozone. And what actually happened here is that the ozone hole over the Antarctic split into 2 different lobes, which you can see here and here. So we have this splitting of the ozone hole, which if we just looked at our numerical model forecast, we couldn't see that happened. If you just look at the data on the right-hand side, it's very hard to say, the data on the left-hand side, it's very hard to see that that's what happened, this splitting of the ozone hole. But by combining these data with the numerical model into what we call an assimilated product, we can get our best estimate of the state here, and we can see what actually happened with this splitting of the ozone hole. So this is just an example as motivation of how using data assimilation can really help us understand about the processes that are happening in the atmosphere. But data assimilation is used on a daily basis to initialize our weather forecast every 6 hours or every 12 hours. So why don't we just use the observations? Why do we need to combine the observations with a model? Well, there are various reasons. The first one, which we saw also in the example of the ozone picture a moment ago, is that we may only observe part of the state. So these are the standard observations. This is from a few years ago, but it's very similar now, of the kind of observations that go into our weather forecasts. So on the left, we have observations at the surface, and you can see we have these come from land measurement stations, from ships, from floating buoys. You can see we have good coverage over Europe, over North America, over parts of Asia, but there are huge areas of the globe where we have very few data. And then if we go higher into the atmosphere, so sometimes we launch balloons to say what is the temperature and humidity structure of the atmosphere, and you can see, if you can see, there are a few dots on this picture on the right-hand side, but you can see that the data are very few, much sparser than even at the surface. And if we're going to initialize a weather forecast model, we have our model with all our grid boxes at the surface, but all the way up into the atmosphere, up into the stratosphere. And we need to know what is the temperature, the pressure, etc. in each of these grid boxes in order to start our model forecast. So the observations themselves alone do not provide this information. We need to combine them with some kind of model forecast. The second reason why we can't just use the observations is that we may observe, we don't usually observe exactly what we're modeling, but we observe some function of what we're modeling, and sometimes a very nonlinear function of what we're modeling. So a standard weather forecasting motion model, for example, will model temperature and humidity, while satellite measures is the radiance that's emitted at different wavelengths at the top of the atmosphere. Now, there is a relationship between that and the temperature and humidity structure of the atmosphere, but it's a very nonlinear, very complicated relationship, and so we cannot just take the radiance measurement and say, okay, this is the temperature we need to initialize this grid box here. There's a complicated relationship, and we need to use techniques in order to do this inversion process that you've already heard about, in order to understand what do those radiances tell us about the actual structure of the atmosphere. And to give an example of a simple way of doing this, and also to introduce some notation, let's suppose our model state consists of just two components, U and V, where U is the east-west component of the wind, and V is the north-south components of the wind. So as in this diagram here. This is quite common in a weather forecasting model. You will model this separately. But normally, when we go out and measure the wind, we don't measure the east, west, and north-south components separately. We may say measure the wind speed, which is W. Now, how is that wind speed related to the variables we're trying to model? So we have an observation Y. I'm introducing some notation here. X is our state vector. So X holds all the variables of our model. So at all the different grid points, our winds, normally our temperatures, etc. Here it's just two wind components. Y is our observation, which is the, in this case, the wind speed. And we have some relationship, which we call H, which takes our model state and converts it to the equivalent observation to say that is what the model, the equivalent of the observation, which we can compare with our real observation. So in this case, to calculate if we had our model state U and V, to calculate the wind speed, we would have to take the square root of U squared plus V squared. And that would give us our wind speed as predicted by the model, which we can then calculate with our measured wind speed and see how well they match and make a correction. And this H, which will come up again, is known as the observation operator. You'll see that this can be in this case, it's a reasonably simple one. In some cases, this H can be very complicated. So if our X is our atmosphere model with our temperatures and humidities, and our Y, the observation, is a radiation at the top of the atmosphere, then H is contains a radiative transfer model which converts all our temperatures, our model equivalent, or our model temperatures and humidities, etc., converts that to the equivalent of what the model would predict the radiation at the atmosphere to be at the top of the atmosphere to compare with the observations. So this H operator can be very simple or it can be very, very complicated in practice. So I've said we can't use the observations, just the observations, to initialize our model. First, because we don't have enough of them, they're sparse. Secondly, because they're a nonlinear function of the state. But thirdly, we also need to allow for uncertainties. So our observations, we know, are not precise or have different precisions, they have errors in them. We know our model state have errors in them. And ideally, we want to combine all these different sources of information, taking into account the relative uncertainties in the different pieces of information. So to give an example of that, I'm going to look at a particular example where, that's not too small, suppose we have an estimate, a prior estimate or what we call the prior we often refer to as the background, estimate of the temperature in this room, TB. And we've got some measurement. Somebody takes the thermometer and measures the temperature in this room and says the measurement error is TO. The measurement of the temperature is TO. Given those two sources of information, what is our best estimate of the temperature in this room? Now, you may at first sight say the observation because we've measured it, but of course the observation has uncertainties. So you may say, well, let's take an average of TB and TO, which may be the case if they have the same uncertainty, but if the observation is more accurate than the background, we may want to give more weight to that. So how are we going to combine these two bits of information in the best way? What's our best estimate of the true temperature? I'm going to take a few minutes to work through this mathematically. So this is what's called a minimum variance analysis. We consider our best estimate. So we're going to assume something about these measurements. We're going to assume that the measurements are unbiased. What does that mean? So if we take the observation of the temperature, TO, it will have an error. Any thermometer has an error. So sometimes it will measure too warm, slightly too warm warmer than the truth. Sometimes it will measure slightly cooler than the truth. But we hope that on average, over lots of measurements, the error will be zero. If not, we would say that there is a problem with our thermometer. So the idea of unbiased means although we know that errors in the measurement, taking the average over lots of different realizations, we can say that the average error would be zero, even though in one case it won't be. We're going to assume that the errors are uncorrelated, so that the error in our background is not related with the error in our observation. We'll also assume in a moment that we know something about the uncertainty. So any measurement device, say a thermometer, will usually come with from the manufacturer with some kind of standard deviation, saying this is the uncertainty, the standard deviation of the measurements, plus or minus a certain amount. And so we're going to assume here that we know something about the standard deviation or the variance, the square of that, of the measurement and of the background. So given these assumptions, what can we say about our best estimate of the temperature? And just to introduce a bit of terminology here, when we combine this prior or background with the observations, the resulting product, of which we call our best estimate, is known in data assimilation as the analysis, which is a strange word, particularly for a mathematician, but it's known as the analysis. And the analysis is what we're trying to get to as our best estimate of the truth. So what we're going to assume here is that we're going to say that our analysis, TA, our best estimate, is going to be some linear combination of this background temperature and this observation, where alpha B and alpha O are parameters that we need to choose. So we're going to take some kind of linear combination according to these two parameters. And the question is, how can we choose these two parameters? Now we've got two unknown parameters, so we need to impose two conditions. So what conditions do we want to impose on our analysis in order to try and constrain what these parameters should be? The first thing we're going to say is that we've assumed our background and our observation are unbiased. We want our analysis to be unbiased. What does that mean? So we know our analysis will not be exactly equal to the truth. Sometimes it will be warmer, sometimes it will be cooler, but we hope that on average, if we do this process many times, the average error in the analysis will be zero. So we want to try and impose that. So let's assume that the temperature, the analysis, is equal to the truth plus an error epsilon A. And the background is the truth plus an error epsilon B, and the observation is equal to the truth plus an error epsilon O. And of course, in any one case, we have no idea what these errors are. We can just say something about their statistics. So we say, well, we want to impose that the average error, and these brackets indicate the expected value, which is essentially just the mean, or the average error. We want the average of our analysis error to be 0 over many realizations. So what is the average of our analysis error? It's the difference between our analysis and our truth, just using the equation at the top of the slide, the first one. But our analysis, we've said, is going to take this form here of the linear combination of the background and the observation. So I'm just going to substitute that into here. We have the the analysis is equal to the linear combination of the background and the truth minus the truth. Now, how are we going to impose that this is always going to be 0, that the analysis error on average will be 0? Well, we need to do some manipulation, because what we've assumed is that the expected value or mean of epsilon b and epsilon o are 0. In other words, that the background and the observation are unbiased. So we can do some manipulation. What we want to do is essentially express this second line in terms of the errors. We can do some manipulation where we subtract alpha b times the truth here, and we subtract alpha o times the truth here, and then we add them back on again here. Now, why does that help? Because here we've got tb minus t truth, and here we've got to minus t truth, which is simply our errors from here. And we know something about the errors. We don't know anything about tb and to, but we do know something about their errors. So we have the expected value of the analysis error is alpha b times the expected value of the background error plus alpha o times the expected value of the observation error plus this term times the expected value of the truth. If there's any questions, please feel free to shout out while I'm doing this. So what we want to do is to choose, what we're trying to do is to choose these parameters to ensure that our analysis error on average is going to be 0. Now, these terms in red, the expected value of the background error and the expected value of the observation error are 0, because we've assumed that our background and our analysis are going to be unbiased. And therefore, in order to ensure that the expected value of epsilon a is 0, we need to ensure that this last term is 0. Now, the expected value of the true temperature could be anything. We can't ensure that's going to be 0, and hopefully it's not going to be 0 Kelvin in this room, otherwise we've got a problem. So, how are we going to assume that the expected value of epsilon a is 0? Only if we choose that alpha b plus alpha o minus 1 is equal to 0. So this introduces a constraint by our two parameters. In order to ensure that the analysis is unbiased, we need to ensure that the sum of our parameters is equal to 1, which gives this equation at the bottom. So now alpha O is equal to 1 minus alpha B. So in order to ensure, by saying that we want the analysis to be unbiased, we've now reduced the fact that instead of having two parameters to estimate, we now have just one parameter to estimate. We say our analysis, our linear combination, must be of this kind of form here. But we still have one parameter to estimate. So how are we going to do that? We want to ensure, all we've done so far is say we'll take the linear combination, which gives us an unbiased estimate. But this unbiased estimate, it could have a small uncertainty, or it could have a very large uncertainty. So we don't know what the uncertainty on this estimate is. All we know is that its mean error will be unbiased, will be 0, because it's unbiased. So what we want to do next, in order to try and constrain this more, constrain this parameter alpha b, is can we choose alpha b to say that the uncertainty in our analysis is as small as possible. We want the smallest possible uncertainty in our analysis. And that's what we do. In a sense, we want to minimize the variance. So if we assume we know the variance of, which is the square of the standard deviation, we know the variance of our background error, which we're going to call sigma b squared, and we know the variance of our observation error, which we're going to call sigma o squared, and we want our analysis error, the expected value of the alpha squared, so the variance in our analysis error to be as small as possible. So what we're going to do is to try and let's find an expression for the variance in our analysis, and let's choose the parameter alpha b that makes this as small as possible. So we do a similar thing to last time. So sigma a squared is the expected value of our analysis error, and our analysis error is TA minus t truth, as we did last time. We can then fit in the linear combination, but that's now this linear combination. We've no longer got the alpha O because we've already constrained this. So we've got alpha b times tb plus 1 minus alpha b times to minus t truth. And then in order to get things in terms of errors, we again do the similar thing as we did before by subtracting alpha b t truth and adding it back on here again. And you can show the manipulation, and you can look through these slides later, that this shows we get down to the expression, this expression here, alpha b times epsilon b plus 1 minus alpha b times epsilon o squared. And if we square this and take expectations using these facts here, and using the fact that we've assumed that the background and observation error are uncorrelated, so that the expected value of epsilon b times epsilon o is 0, we get this expression for our analysis error. And then what do we want to do? So this is in terms of our background error. This is the variance of our analysis error in terms of the variance of our background error and the variance of our observation error. And we want to find the parameter alpha b that minimizes this. How do we do that? Well, simple calculus. We take the derivative with respect to the parameter alpha b, set it to 0, and find what value of alpha b gives us the minimum value. And that gives us this sigma o squared over sigma o squared plus sigma b squared. So where does all that lead to? That's quite complicated. What we end up with is this expression, that TA is sigma o squared over the sigma o squared plus sigma b squared times the background temperature plus sigma b squared over sigma o squared plus sigma b squared times the observation. And this is our best linear, what's called the best linear unbiased estimate, sometimes shortened to blue. Best in the sense of it gives us the minimum variance. It's a linear estimate because it's a linear combination of the background and observation. And it's unbiased because we've shown that the expected, or we've constructed this so that it's unbiased, so that the expected value of the analysis error is 0. But let's just have a little look at that. What happens if the background and the observation have the same uncertainty? So sigma b squared is equal to sigma o squared. Then you see that what we get here is TA is just a half of TB plus a half of TO. So if they have the same uncertainty, we just take the average of them, which it would make sense. What happens if the observation is a lot more accurate than the background? So that means sigma b squared is a lot larger because the background is more uncertainty. Then we give more weight to this term, and so we give more weight to the observation. Whereas if the observation is less uncertain and the background is more certain, so that sigma o squared is large, then we'd give more weight to this term and to the background. So you can see that what we've constructed here is an estimate of, given the two pieces of information of a background estimate of the temperature in this room and an observation with their uncertainties, we've constructed this estimate which allows for the uncertainties in each of them. If they're the same uncertainty, we'll just average them. But if one is more uncertain than the other, we'll give more weight to the piece of information which has more certainty. And interestingly, we can find what is the error in our analysis, so the variance, is less than or equal to, this should be, the minimum of our sigma b squared and sigma o squared. In other words, that our analysis is at least as good, on average, as the most accurate piece of information we have. So if the observation is good and our background is terrible, the analysis variance will be at least as good as the observation variance, and the other way around. Happy, more or less, with that? If you don't follow the details, you can follow them later, but what I wanted to give the idea is, so we've got two pieces of information, a background with some measurement of its uncertainty, and an observation with some measurement of its uncertainty. And we can find a way of combining these two bits of information in an optimal way, where we define optimal as being unbiased and minimizing the uncertainty in our estimate. Now that's with just a simple temperature. What happens when we go to a much larger system, like a global weather forecasting model, where we've got 100 million variables and a few million observations? How can we do the same thing? And in order to generalize the problem, we need to use probability distribution functions, or PDFs, to represent the uncertainty. So this is a PDF example of just saying this is x, some state x, and this is the probability of having the certain value of x. And what we want to do is combine these, use this information, assume that we have a prior estimate or a background in general, and we have observations. But instead of just having now the mean is 0 and uncertainty is a variance, we're going to have a probability distribution function. So we assume that we have a prior distribution of the state x, or a background, and we're going to call that P of x. And we assume we've got a vector of observations, y, with conditional probability, the probability of y given x. So we're going to assume that we have something. So what does this mean? So for example, the prior distribution in our previous example was saying we assume it's essentially Gaussian with a mean TB and a variance sigma b squared. And the observations, we said we assume it's Gaussian with a mean TO and a variance sigma o squared. And this is just a generalization of that. Then Bayes' theorem, what we want to know is, given these pieces of information, is what is our best estimate of the state given the observations. And Bayes' theorem says that the probability of the state given the observations is equal to the probability of the state times the probability of the observations given the state divided by the probability of the observations. So this is what we call the posterior estimate, or the posterior PDF, is equal to, this is just what we had as a prior, our probability of the state. We have the probability of the observations given the state, so that's our information about the observations, and this is often referred to as the likelihood. And then the probability of y on the bottom is, it doesn't depend on x, and so this is essentially just a normalizing constant. And so we'll use that fact, because we don't know what this is, we'll use the fact of proportionality, that we know that the left-hand side here is proportional to the top of the right-hand side here, and we'll ignore the normalizing constant in what's to come. And what does this mean? Let's give it a little example. So what essentially this means is that if we've got the prior, so we've got a PDF representing our prior, and we've got a PDF representing our likelihood, all we need to do is multiply them together, and we get our posterior PDF. So let's have a look at some examples, and in the practical tomorrow there'll be some simple examples to play with like this. So here, the solid blue curve is our prior. Let's say this is of the temperature outside, although outside in winter, certainly not outside now. So the prior is saying the temperature is around -2. It has a mean of -2 and has this uncertainty. The likelihood, so that's our prior estimate. Our observation, or our likelihood, is saying the temperature is +2. So what happens if we just take these two things and we just multiply the values together in each column, each value of x? We get the red curve. And what we see here is this is our posterior, and we see that the mean of this is 0, which we expect. The prior says the temperature is -2. The likelihood says, or the observation says the temperature is +2. We see by the width of the blue curves that they have the same uncertainty. And so what we're essentially going to do is to take an average, and we get something in the middle, which is 0. What happens now is similar one. So now our prior here is saying something like is +3, and our likelihood, our observation, is saying is +1. But you notice that this dotted curve is much narrower than the curve of the prior. That's telling us our likelihood is much more accurate, our observation is much more accurate than the prior. So we'd want to give more weight to the observation. What happens when we multiply those two together? We get the red curve here, which you see is not equal to the observation, because we do have some information coming from the prior, but it's closer to the observation than the prior, because we're taking into account the fact of the relative uncertainty in each of them. And what you'll also notice is this red curve is narrower than any of the other two curves. In other words, as I said that we showed theoretically, the uncertainty on our analysis is better, is narrower, is smaller than the uncertainty on either of the two pieces of information going into the estimate. What happens here is an interesting one. So the prior is bimodal, is this blue curve at the bottom here. So the prior is saying, I think the temperature is either plus or -2, but I have no idea which. The observation says, well, I think the temperature is +1. So the observation, and it's got a very narrow width, so the observation is fairly certain. So the observation is saying, we're definitely positive, and I think the value is +1. So here we're then going to say, we're definitely going to move to the positive side, but we're still going to average between the observation value and the prior value here. And so we get the red curve here, which says our estimate, our best estimate, is just above +1, but it's definitely positive. And you see here, we have very little probability of the observation of the state being negative, because the observation is telling us more or less that it's definitely positive.
But it's still shifted slightly the wrong way somehow.
It's shifted slightly to the right because essentially it's taking the average, it's taking account of this, but also of this value, this prior value here.
So it completely ignores the bulk of the prior.
Yes, because the prior, if you look at the likelihood here, is close to 0. So if you look at this formula here, the prior on the left-hand side is being multiplied by the likelihood, and if the likelihood is 0 here, which is the blue dotted line, then it's just being multiplied by 0. So the likelihood is essentially telling us there is no chance of the state being there. And so when we multiply them together, that becomes 0. Does that make sense? Okay, that's very nice in one-dimensional PDFs. In practice, we have PDFs which are of dimension 10 to the 9 or more. So that means it's impossible to do what I've just done in practice. We cannot calculate the full PDF. We couldn't hold it in a computer memory. We couldn't even try and understand what it is. So we need to either calculate an estimator based on the PDF or generate samples of it. In other words, I'm going to say I want to approximate what the PDF is, either by saying I'm going to just take samples from it, or I'm going to say an estimator means I'm going to just calculate the mean of the PDF or the mode of the PDF or something like that. So how are we going to do this in practice? And in practice, what we're going to do, let me stay on here, is we're going to make some simplifying assumptions. And these simplifying assumptions are made in most weather and ocean assimilation systems and most assimilation systems at the moment. We're going to assume everything's Gaussian. Now, what does Gaussian mean? So if we looked at the scalar case, so when I showed about the temperature in this room, all we needed was two pieces of information. Its mean, that the mean error was 0, and its variance. And that told us everything about the uncertainty, everything about the information. When we take this to multi-dimensions in a Gaussian, what we need is the mean, again, and the covariance, a covariance matrix. And a covariance matrix just says is the covariance between different elements of the state. So I can have, say, if I look at the temperature of this room, the variance is how this temperature in this room is related to itself, its uncertainty. The covariance says how does the temperature in this room relate to the temperature outside, which is the covariance. And we have a matrix of these things. And these are the formulae for the probability distribution functions when we look at the Gaussian. But I'll look at these in detail to explain. What we have here, so first the prior. We're going to assume that the prior has a mean xb and a covariance matrix P. Now what does that have here? Essentially, if this was a scalar, we would have x minus xb squared. So this is the Gaussian formula you may know in the scalar case. You end up with x minus its mean squared divided by its variance. Here, because we have the multi-dimensions, we have x minus its mean squared in a certain sense in terms of vectors. Instead of dividing by variance, we have the inverse of the covariance matrix P here. So we're taking the exponential of this, and then we end up with a formula 2 pi n is the size of the state, and this here is the determinant of the covariance matrix. So what we're going to assume here is that we know xb, so we know the mean of our state, which is essentially the tb that we had before, and that we know the covariance matrix P, which in the scalar case was just assuming sigma b squared. And we have a similar thing for the likelihood, P of y giving x. So now we have the difference between y and our x. And here, the observation operator I came across, I introduced before, comes in. We have y minus h of x. Why don't we just have y minus x? But as I said earlier on, we don't necessarily observe the full state, and we don't necessarily observe the things we're modeling. We may observe some kind of function of our state. And so what we need to do is to take our model state and convert that to the observation, equivalent observation, to be able to compare with the observation, as I did with the example of the wind speed earlier. So this is what this h of x is doing. So in that case, y was the wind speed, x was our u and v components of the wind, and the h was the square root of u squared plus v squared. So here we need to take the difference between our observation and our model prediction of the observation using this h. And again, essentially we're assuming that the mean of the error in this is 0, and we divide by, we assume that we know something about the covariance in the observations, which I'm introducing this matrix R here. There's notation, by the way, so Y for the observations, R for the observation covariance matrix, and H for the observation operator is a standard. So now in data assimilation literature, there's a standardized notation, and this is the kind of thing. So I'm introducing this here also to introduce some notation that you will see again, and if you read the literature, you will see this. So assuming that we know on our prior, we're assuming we know its mean and its covariance, and the likelihood, our observations, we're assuming we know that the mean error is 0, and we know the covariance. What we need to do by Bayes' theorem is simply multiply these two together. So if we ignore these constants at the top, we've got the exponential of one thing times the exponential of another thing. And so the exponential of one thing times the exponential of another thing is simply the exponential of the sum. So we say that I'm going back to using this formula here, that the probability of x given y is proportional to the product of the probability of x and the probability of y given x. So the probability of x given y is proportional to this times this, which is equal to, if we ignore these constants, is proportional to this. We're taking this minus a half out, and we have essentially this term plus this term, because I've just taken the sum of the two terms. Okay, that's all very nice mathematically, but as I said, these are huge matrices and we can't actually calculate that. What can we actually do with this? Well, one thing we can try to do is to say, okay, what's called the maximum a posterior probability. If we assume everything's Gaussian, we can say, okay, this is our probability distribution. For this, the mode is equal to the mean. So let's try and find the value of x, which gives us the maximum probability. That's our most probable state, x. We may not be able to find the full PDF, but let's try and find the most probable state. How are we going to do that? Well, we've shown that our probability of our state given the observation is proportional to this, simply by multiplying the PDFs. So here we have minus a half times something positive here, because this is just essentially x minus xb squared, and this is essentially just y minus h of x squared. I should have said that this, in the scalar example, this y would have been our observation TO, and our r would be the variance sigma O squared. So, what is the x which maximizes this probability, which gives us the probability? This p of x given y is the plot here. What is the x, value of x, which maximizes this? Well, since this is the exponential of minus something positive, the value of x which maximizes this is going to be the value of x which minimizes what's in the curly brackets. In other words, what minimizes this function here. So the maximum probability, the state x, which maximizes this probability, is going to be the state x, which minimizes this expression here. That makes sense? Say that is a yes. Hopefully.
Can I ask questions?
Yeah.
Are there any questions so far? If you don't ask now, you'll just get even more lost. Okay, and you can watch the replays. So.
And hopefully we'll become clearer in the practicals as well. Well, what we've basically got down to is saying, if I assume that I have a background state and I know it's mean XB and I know it's covariance, and I assume I've got observations and I know that their mean error is 0 and I have their covariance, my best estimate of the state under the assumptions that are Gaussian is going to be the x that minimizes this function. And if any of you have done least squares analysis or least squares estimation, you'll see that this is simply a least squares function. I'm saying, what is the x which is closest to the background, weighted by the inverse of its errors, and closest to the observations, weighted by the inverse of its errors? So in a sense, all that I've gone through is a way of showing that we get down to something under these assumptions, which is essentially a least squares estimation. And so what the data assimilation problem comes now is, okay, assuming all the assumptions we've made so far, what is the x that minimizes this function? Now, if we assume h is linear, then this is a linear function. We can take its gradient and we can write down the exact solution. So the exact solution under the fact that it's linear is given by this here. However, we can't calculate that in practice because I've said this P will be a matrix of order 10 to the 9 times 10 to the 9. So we can't even hold a matrix like that in memory, never mind try multiplying it. And this R matrix will be at least a few million by a few million, maybe simplified, but we cannot treat the problem exactly like this in practice. But this gives us some ideas of how we may approach the problem. So how are we going to solve this in practice? We want to actually try and minimize this function, or if h is linear or approximately linear, try and solve this equation approximately. And these introduce the different methods that we solve in practice. So the variational methods, which we'll again look at tomorrow, is saying, okay, this is the function we need. Let's just use some kind of numerical optimization method and find the x that minimizes this function. What does that mean? So suppose we're having one dimension, this is x, and this is our function j of x, so it might be a complicated function. We start at some point, we say, what is the value of the function j and its gradient at that point? And we use an iterative method, which gives us an updated value at this point. And then we say, okay, what is the value of j and its gradient at that point? And we use that to get a better estimate. Another point, and we keep iterating using these iterative numerical minimization methods until we get close to what's called, as close as possible to an optimum. And that is the practice of variational methods. And this, we'll go into more detail about how to do this tomorrow. But it's the method used in practice by centres such as ECMWF or the UK Met Office. Usually in this case, we assume that P, this matrix P, is constant and is often denoted B. But note that in order to do this, on each of these iterations, we need to know the gradient of this function, known as this cost function. And that can be complicated in practice. And we'll go into that again in more detail tomorrow. Or we could solve exactly, if we're assuming the linear case, the equation I found for the linear case. And this is what's known as the Kalman filter. It's only exact for the linear case, but what happens here is instead of keeping this matrix P covariance constant, we update it. And again, we'll see more of this tomorrow, why we update that. But we can update that saying what is the uncertainty in our latest estimate of the background and how can we calculate that. And that will, that's the Kalman filter, and hopefully that will become a bit clearer tomorrow looking at this. And although this is true for the linear case, it can be extended to the nonlinear case by linearization. But in practice, again, this, as I said, this involves the multiplication of very large matrices. So we can't actually do this except for some small problems. I mean, some of the smaller problems, so some of the chemical data assimilation, for example, or land surface, you may be able to do these kind of problems on. But otherwise, what can we do? We have this evolution of this covariance matrix. What we can do is approximate that by an ensemble of states, and that leads to the ensemble Kalman filter, which again we'll go more into tomorrow. It's similar to the Kalman filter, but instead of doing this multiplication by huge matrices, it takes a series of nonlinear forecasts, an ensemble, and it uses a forecast of those in order to approximate this covariance. So instead of having this huge matrix, we just have a few forecasts and approximate the covariance using those. And again, we'll go into more detail about that tomorrow. There is another method that we won't go into, which uses a weighted set called particle filters that you may have come across, which tries to sample from the PDF and then weights those samples according to how likely they are. And as in the Ensemble Kalman filter, it uses an ensemble of forecasts. But the interesting thing about the particle filters is that it doesn't make the Gaussian assumption. And all the other methods I've shown all assume that everything's Gaussian, which in practice, for some applications, we know is not true. So people are more and more trying to develop these new nonlinear methods which don't assume that, such as the particle filter, and to make them efficient. But I won't go into any more of that in these lectures. Finally, just to say about how you come across these terms filter and smoother, there are two ways of considering how we've got how we treat the observations. If the observations are these stars in time, we can consider that we make a forecast. When we get to an observation time, we combine that forecast with the observation to get an analysis. And then we make another forecast until the next observation time, combine that forecast with analysis, with the observation, sorry, to get another analysis, and so on. And so we treat the observations sequentially in time. And the Kalman filter is an example of this. But an alternative is that we try to find a state, we treat all the observations together, and this is known as a smoother, where we're just trying to find a model trajectory through the observations. And some of the variational methods I'll talk about tomorrow use this. So we will see both methods tomorrow, the filter method and the smoother method, which are different ways of treating this. So just to sum up, data assimilation, why do we want to do this? It provides the best way of using the data with the numerical models. Our data alone are not enough to initialize forecasts or to really understand. Our numerical models alone are not enough, but this data assimilation provides an optimal way of combining them, taking into account what we know, taking into account the uncertainty, taking into account the physics of the problem, etc. A natural way of expressing this problem in theory is Bayes' theorem, which simply says all we need to do is multiply two probability distribution functions, and it gives us the information we need. But in practice, we cannot treat it like that, and in practice, the problem is more challenging. And this is the story of the next lecture, where we'll look at how in practice we can solve these variational methods, and we can solve these ensemble Kalman filter methods. I think that's enough today.
Thank you very much. So any questions on that? Yep.
Hi. You mentioned that some cases are known not to be Gaussian.
Yes.
Well, can you give an example of some of those? Or
Okay. So when things are, the Gaussian assumption assumes that things are quite linear. So as you introduce more physical processes, for example, which are very nonlinear, then the Gaussianity assumption can either fail or may only be true for a short time. So one example, for example, is forecasting in the atmosphere of convective storms, so thunderstorms, etc., which are very localized and very nonlinear. And the linearity assumption may hold for 5 minutes or so, but it's not very. If you want to look over a long window, you really need to take account some of these nonlinear processes. But also, as we go to more and more high-resolution models, you realize that the linearity assumption breaks down. So the atmosphere is fairly linear on large scales. When we get to very small scales, it can become very nonlinear.
Thank you.
I think in order to apply data assimilation, you must have good knowledge about the process you are trying to understand or to map. But sometimes that is not possible. So where can you put the threshold of applicability, you know?
I think what you essentially need to do is you need to have, you're trying to combine a model with the observations to try and keep your model on track. So the question is, can your model reasonably represent the observations? If it can, first, can your model reasonably represent what's happening in the world, the observations? And can you somehow quantify, even approximately, the uncertainty in your model forecast, given the observation, the uncertainty in your model forecast? And if you can do that, then I think there is a possibility to do this. I think where it will break down is, I know there are some things where maybe the models are much less developed now than the observation, and therefore then it becomes more difficult because your observations are really much more accurate. Although there are ways of using these methods also to improve your models, for example, to estimate parameters in your models.
Okay. Yep.
So in this process of assimilating the observations, what would be the effect if your observations are not very well distributed in space? So especially like in regions in Africa or wherever, where you just have a single observation with the effect when the uncertainties for that observation are actually quite large. Yeah. And you might not even know about it or the quality of the observations. So Can you say something about the effect of well, what we know about the uncertainty of the observations, which is not always clear, I suppose?
Yes. I mean, that is one of the big problems, and I think you have to assume, well, there's a couple of things there. One is that the uncertainty of the observations, you have to assume that you know something about them. And in a sense, this data assimilation method assumes that you know something about your uncertainty. But what we find is, I mean, often things are approximate, so we often assume that observations are not errors are not correlated, which we know they are, and people are trying to look into that now more and more. But even with the basic assumptions, sometimes you can get some information into your model. Then there's also the question about them being sparse, and what you can do is, so there are things, and you'll hopefully see this in some of the practicals, you can design by the way you design these covariance matrices, you can say how far do I want to spread the information about a particular observation. So it may just tell me something about that point, but it may spread something quite widely. So you can also use the observation to spread things more widely if you believe it's more representative of what's happening around.
Anyone else?
Going off that point then, is it sort of safe to assume, like with global models like ECMWF, when they validate their models, obviously they use observations which are generally a lot more dense over Europe. Would it be safe to say then that the weather forecasts are better for places where observations are more dense?
Yeah, I mean, it depends. I mean, how you validate the models and whether you validate against observations or analyses is difficult. So you're thinking about what happens if I try, what are the forecasts like where I don't have observations?
Yeah, is it sort of systematic that the models are better over like Europe and
you would have more accuracy over that, yes. But the other thing is, within the space of a few days, information can be carried quite a way from observations. So that's why if you're doing, say, 4 or 5 day forecasts, it's observations over the states and not just off the states, which are influencing what's happening, how good the 5 day forecast is over Europe, for example. And so you need to also think about this time thing, about the time of the forecast and the way things are propagating.
Anyone else? Okay, I just have a quick question. So in 2012, since 2012, we've been in this new kind of golden age of machine learning.
Yes.
And I guess that in numerical weather prediction, this must be having a huge impact. Now we can use deep neural networks to improve, I guess, data assimilation and.
To be honest, so far there has not been much in that. I know a couple of people who've started looking into whether we can combine machine learning with data assimilation. And I think that is one of the interesting questions for the future. I don't think there has not been much done so far in that. There's been 1 or 2 studies. I mean, I think part of the question is, I must say I don't know a lot about that area myself. I think part of the problem is how big a database you need and how many things for such large systems. How big a training set you need.
Yeah.
But I don't know enough about that myself to really comment.
Okay, thank you. Yes.
And to some extent, I think machine learning is oversold. Machine learning is what you do when you don't know what to do. Right. Okay? So, and by the way, that was, it's not my quote, it's from people who... Yeah, so, no, some problems, if you have a lot of control over if you know a lot about it, like the atmosphere, it's physics, chemistry, you know equation state, all the rest of it, you've got a lot of control over your problem. So why would you want to go to machine learning that knows absolutely nothing about that? If you have issues over the land where you've got where you've got tenuous correlations and so on, and you really can't put all the connections together, then or the problem is just too complicated to solve by the sort of things that Amos is talking about, then maybe you do go to machine learning. But for me, I'm old school. It's a last resort for me. Okay.
I mean, that's true. It's interesting. One thing that I couldn't cover in this, but in practice, in the algorithms I mentioned, we do build a lot in of the physics of the problem, and so the equation of the problem, how things are related, etc. So, how are things related? For example, how is the wind and the pressure related? When you have a low pressure, the wind goes in a certain direction. How do you can build that into your simulation systems so that pressure is telling you something about wind and these kind of correlations. And I don't know how it is, but I mean, it may be possible in machine learning, but there are practical ways of really getting this kind of information into data simulation systems.
I guess maybe it could be used for certain aspects of the problem,
Yes.
to resolve a particular measurement where you have maybe lots of measurements and you want to feed that into a larger model, then maybe it could be useful. But okay.